Right. Okay, students. Are you ready for our class today?
Yes, sir. Yes, sir.
All right.
Yes,
Good.
sir.
Yes, sir. Ready.
All right. Let me remind you for today's session. This is a session for collaborative teaching, STA250, for the topic of Neyman-Pearson Lemma. Right. So I hope you can learn as much as possible from Dr. Irfan, Dr. Muhammad Irfan. Uh, he is our guest lecturer from University Kebangsaan Malaysia. Right. As I told you before, please switch on your webcam during the session. And if you have any question, then you can voice out the question. Make sure the question is precise and related to the topic. All right. Let me introduce our guest lecturer. Our guest lecturer name is Dr. Muhammad Irfan Abdul Jalal. He is a senior lecturer at the school at the University Kebangsaan Malaysia. Right, he is a medically qualified and highly dedicated medical statistician with more than 8 years of experience in applying various basic and advanced statistical methodology, including Bayesian statistics in clinical research, specifically in field of oncology and therapeutic drug monitoring. So, in addition, he is highly proficient in complex data analysis and interpretation with expert knowledge in good clinical practice. Uh, and he also have extensive programming experience using R, SAS, and data analysis using commercial statistical platforms such as SPSS, Tata, and Minitab. So he also has a significant publishing track record and experience in postgraduate supervision and undergraduate teaching. He also a multitasker as an as a evident from multiple role assumed and responsibilities and trust during employment and studies. So without further ado, before we call our guest lecturer, can we take a selfie for this session? Can you switch on your webcam now? Okay, tunggu lagi yang lain. Tolong switch on your webcam. Adriana, Ahmad, Aina Shafika, Elisa Sofia, please hurry up. Okay, I think should take take our picture now. So smile. Right, 1, 2, 3. Right. Okay, thank you very much. And I for to start our session today, so I pass over to Dr. Muhammad Irfan to start our the lecture.
Okay, Assalamualaikum and a very good morning to everybody. Can you all hear me? Can you all hear me? Is it okay?
Yes, yes, yes.
Okay. Okay. Right. Okay, my name is Dr. Muhammad Irfan. You can call me Dr. Irfan. I'm from UKM. I'm currently working in one of the research institutes in UKM. I'm officially the biostatistician or the medical statistician under my institute. So far, without further ado, then we just proceed with our lectures because there are several things that we need to cover today. Sorry. Sorry. Something wrong with the computer now. Sorry, Dr. Nasir, I cannot move my slides now. Yeah, sorry. Some technical problem.
Kalau tak tak buat slideshow pun tak apa.
No, I cannot find my cursor here. It's stuck. Okay, sorry. Because I just approached somebody to annotate the slides, so I cannot really move the slides now. Yeah, sorry.
Oh.
Yeah.
Kejap, maybe you can unshare and reshare again.
I cannot see my my cursor here. Sorry. Oh yeah. Okay. Right. Nah, the slides moves now. Can you see this? Can you see the slides? Okay. So let me introduce first to the what is Neyman-Pearson all about? Because so far, just a brief overview. In our classical or traditional frequentist theory of hypothesis, the theory of hypothesis testing is deeply rooted in the Neyman-Pearson Lemma, because as your lecturers, Dr. Nasser has told you before, in statistics we can divide the current paradigm or the current framework into two. It's either frequentist or the Bayesian theories. But for the the classical view or the frequentist view, we are going to cover the frequentist theory of hypothesis testing today. So we are going to cover how we test the hypothesis based on the frequentist setting. So we're going to disregard all the Bayesian stuff. So under this framework, we limit ourselves to testing to test statistics for which the probability of type 1 error is less than or equal to a specific constant alpha. Where in this case, in the frequentist theory, we fix type 1 error or our alpha level to a certain values, and we want to our next task is to find a region where it will give you the highest power for this statistical test. So the point number 3, a critical region for testing a simple null hypothesis where value is equivalent to your other alternative your parameter values assume under the alternative hypothesis is said to be the best or the most powerful if the power of the test at the alternative hypothesis value is at maximums. So in this case, we preserve the type 1 error to certain values, but our task is to find a critical region or a region where we can say that the power of our statistical test is at maximums. So before we proceed further, let me give you an overview, but again, a recap. What is alphas and betas are all about. The type 1 error and the type 2 error are all about. So it can be summarized in these simple diagrams. For example, the truth or the actual things that happens in the universe or happen in the nature, there are like two things. It's either the null hypothesis is true, which means that there's no like significant difference in two things, in two things with respect to certain outcomes. And then the H naught or the null hypothesis is false, where we can say that there's a significant difference in truth in the universe. There will be there's a significant difference in the outcomes parameters between these, for example, these two groups, and that's the truth in the universe. But when you perform your hypothesis test, even though there's no difference between these two groups in truth, well, we can say that H naught is true, but perhaps you can make either you can make either of these two decisions. Either you fail to reject the null hypothesis, and then the truth, which is the null hypothesis, is true. In this case, you make a correct decision because you don't reject a true null hypothesis. So in this case, we can consider this one as 1 minus alpha, or your usual confidence level. But if your null hypothesis is true, but unfortunately you make a mistake of rejecting the null hypothesis, in this case we are committing a type 1 error, or we're committing a false positive of size alpha. In this case, we say that there's a positive effects, or there's a positive differences between these two groups, for example, based on t-test, but actually in truth, in the nature, there's no such a significant difference, and because of this, we are committing a false positive result. I mean, it's a negative result, but we're saying that it's a positive result. There's a difference there. So in this case, we're making a false positive result. Okay. So on the other side, if the null hypothesis is false, so in this case, we accept the alternative hypothesis, then in this case, if we fail to reject the null hypothesis by saying that, okay, the null hypothesis is true based on our hypothesis test, but in truth, in the actual universe or in actual nature, actually the null hypothesis is false, then we are committing a type 2 error. By saying, yeah, okay, there's no positive result, there's no positive differences, there's no significant differences between these two groups, or for example. But actually, there's a significant difference there, so we are making a false negative statement, like type 2 error, which is our beta. But if our result of our hypothesis is we reject the null hypothesis, and actually the null hypothesis is false, so making the correct decision in this case is considered as our power of our hypothesis test, which is 1 minus beta. And then this is our main gist, or our main aim of finding the best critical region where we can optimize or we can maximize the power of our tests. Okay, as another recap, like type 1 and 2 to see things more clearly. When we conduct a hypothesis test, there are two there are two distributions that we are looking into. It's either our test statistics or our mean values, of the parameters. For example, our mean values for the normal distributions. Is either we lie in the null hypothesis distributions or either in the alternative hypothesis distributions. So in this case, we fix the type 1 error region we fix the type 1 error rate to a specific value of the size of alpha. In this case, for example, we always fix to 0.05, even though other values can be used as well. But usually we fix at 0.05. So for the alternative hypothesis distributions, the distribution under the parameters that we hypothesize falls under the alternative hypothesis, we have another set of distributions here. Another distribution here which is given by the by the green curves here. This is our alternative distributions. So the type 2 errors where we make a false negative results there, where we fail to reject the null hypothesis, where actually the null hypothesis is false. We fix the values at some values of beta here. For example, like 0.20 in our usual case in medical statistics. So the opposites of that. So when your alpha is 0.05 and then your 1 minus alpha will be like 1 minus 0.05. So it will be your usual confidence level, or your 0.95 confidence level. And this will be your usual 95% confidence interval. So you can see that there's some a very strong relationship between the 95% confidence interval and then the type 1 error that you fix. There's a very close relationship there. So for the power is 1 minus beta. So if the type 1 error, the type 2 error here is 20%, 0.20. So your usual power will be around like 80%. And you can see that this line here represents the critical, we call that the critical values. And then you can see that there is like a very strong relationship between betas and alpha here, between type 1 error here, and then between the type 2 error here. For example, if you reduce the type 1 error further, for example, you shift the lines here to the right side, then you will increase the type 2 error rate. But if you shift the lines to the left side, in this case, you increase the type 1 error rate, then you will then you will simultaneously decrease the the type 2 error rate. So you cannot really like reduce the type 1 error rate without any repercussions or without any effects to the other types of error, which is the type 2 error rate. So that's the reason why I say that there's a close relationship between alpha and beta in this case. Okay. So for today's lessons, our objectives is this one: to find the most powerful region of size alpha, where our null hypothesis H0 is given by theta equals to some values of the parameters under the null hypothesis, and then the alternative hypothesis where the values of the parameters is equivalent to some values under the alternative hypothesis. But before we proceed to our main lectures today, we need to introduce some ground rules, where we need to introduce the notations and the differences between simple and composite hypothesis, and define what it means to have the best critic region of size alpha of this type 1 error. Okay, so let me introduce to the notations. For example, if you have a random variables, a random sample of size n, which is x1, x2, x3, and then until xn, from distribution with probability density or mass functions. In your case, I think if you refer to probability mass function, it's actually your probability distribution functions. But usually in my practice, we always use probability mass function. So when when I mention probability mass function, it is equivalent to your probability distribution functions. Then the joint probability or the joint probability density or mass function or your distribution function here, x1, x2 until xn, is denoted by the likelihood function of L, theta here. In this case, as you can see, that the likelihood functions of theta, the likelihood of the parameter of given by theta here is equivalent to this one. It's theta given your observation there, which is x1, x2, x3 until xn. And in the same manner, this way, you can represent this likelihood function in this form, where f is your density or your probability mass functions of the observation given your parameters. Make sure that the order is correct. So either you use the given sign here is you can use the semicolon here mathematically, it's fine, or you can use the bar here. So it's also fine. So if you look into like some stats journals, some people they use like semicolon, and then some people they use bars. Then there are equivalent things. But make sure when you use the likelihood function, the parameters always come first, then the observations comes later. And then when you use in the F form, the functional forms, the mathematical functional forms, always make sure that the x comes first and then the parameters comes later. Okay. So as you know, then the likelihood is given by the probability just the mass function of x1 given theta times given x2 given theta until xn given theta. And then one thing that you need to remember, that the likelihood function of the parameters theta still depends on the observation data in the sample. And then for our lectures, PMF or the probability mass function is equivalent to the probability distribution function. So the terminology is equivalent. Okay, so before I proceed, I will talk until like 10:50, and then I will give you a 5 minutes break before we proceed again at 11 o'clock. Okay, so let me introduce to the simple and composite hypothesis. So the definitions. So we always start with definitions in mathematics. So if a random sample is taken from a distribution with parameter theta, a hypothesis is said to be a simple hypothesis if the hypothesis uniquely specifies the distributions of the population from which the sample is taken from. It means that in this case, for example, if you have normal distributions for your simple hypothesis, for example, for your simple alternative hypothesis, if the means and the variance are specified, I mean, they are given certain values there, then you can say that is a simple hypothesis because you can now pinpoint to a certain normal distributions. But it's considered a composite hypothesis if the hypothesis is not a simple hypothesis. For example, if the I mean the values for the parameters are not given, so you are given like a generic normal distribution without knowing what's the values of you know of mu or the means of the normal distribution under the alternative hypothesis. So in this case, you don't really know what is the specific distribution for this normal distribution or Gaussian distributions. So in this case, we can consider that as composite hypothesis. So as an example, let's look how we can solve this problem. Suppose, okay, for example one, suppose that we have a random sample from exponential distributions from x1, x2 until xn with certain parameters theta. In this case, we define or we say that the parameters value under the alternative hypothesis is equivalent to 3. Okay, so do you think so? We need to examine whether this alternative hypothesis is simple or composite hypothesis. So how we do solve these kinds of of this kind of questions. Okay, so for example one, the solution is this. The most important bits you need to before you answer the questions, you need to find the key informations from the example. So in this case, we summarize that in a very simple manner, where the random variables x1 until xn is considered a random sample from an exponential distribution. This one is the main key informations from the questions queue or from the questions. So as you know, from your probability distributions lectures, the PDF or the probability density function, because it's continuous distributions for this exponential distribution with parameter theta, is given by these mathematical functions: 1 over theta exponential values of minus x divided by theta, where we constrain the x values to be positive, 0 to positive, which means that in this case there's no negatives. So and then theta is more than 0. I'm not sure. I think that you will not be penalized if you don't put these things. But for sake of completion, for the mathematical arguments, I mean, always practice when you write a density function for certain things to also include the range of the values that can be taken by the random variables and then by the parameters values. Okay, it's a good practice, but perhaps for your exam it will not be penalized. But okay, as you can see from here, there's there's small notes here. It's a scale parameterization form. So we only have like we use theta for the scale form here. So under the alternative hypothesis, we say that theta is equivalent to 3. So we just substitute that theta 3 into the denominator in here. So the fx or the probability density function for the exponential distribution becomes 1 over 3 e to the power of x minus 3. So in this case, you can see that this distribution, exponential distribution, is a specific distributions because we already like specify all the parameters in here for the exponential distributions. So in this case, we can consider the alternative hypothesis is a simple alternative hypothesis because this is a specific exponential distributions because we really specify the parameters values for the exponential distribution parameters here, which is 3. So it's a simple alternative distributions. So again, as an additional info, you can also specify the exponential density functions in the rate parameterization form where lambda is equivalent to your 1 minus theta. So in this case, because of this relationship, you can put a lambda there. So again, the range that can be taken by lambda is also the same, like thetas. Usually I work with this form, but based on the mark scheme, so I work with the scale parameterization form, and then not based on the rate parameterization form. So if you happen to take, you know, a stochastic process modules or that kind of things during your, during your studies in, in your ITM, or later on, perhaps you, I mean, during your master's years, you'll be doing some sort of like stochastic process kind of works. These relationships is very important. I mean, it's a very special properties of exponential distributions where it has a memorizers properties. For example, if you want to estimate, you want to know what's the probability of an event occurring after time t, given that the events occurs after time s. Okay, when the probability of the events occurs after time s with addition of small time t here, given given the time already passed as minutes or as seconds, then the probability is t is bigger than t. The probability of the of the time, for example, is bigger than t. So that's why it's called a memorialist property. So you can disregard everything before time s, for example. I mean, in this case, s occurs first. For example, this one is 1 minute and t is 2 minutes. So what is the probability of things occurs in 2 minutes? Given that, I mean, the time has elapsed has elapsed for 1 minute, then the probability is what will happen 1 minute after s. So it's nice properties anyway, but it's not relevant to the solutions. But I think, I mean, it's good thing to know. So for example 2, so we proceed to example 2. Suppose that we have another random sample for from exponential distributions where x1, x2 until xn. But in this form, in this case, we specify the alternative distribution and the alternative the values for the parameter of this exponential distribution under the alternative hypothesis as something bigger than 2, which is not specific anymore. So in this case, do we consider it a simple or composite hypothesis? So recall from the previous example, the probability density function of fx is given by these ones. And since HA, the parameter values under the alternative hypothesis is bigger than 2, then the theta values can take any values bigger than 2. For example, theta can be 3. And the PDFs or the probability density functions for the alternative hypothesis, the distribution under the alternative hypothesis will be this one. And if it's theta equals to 4, then the PDF probability density function under the alternative hypothesis is this one, and theta is 5, then it will become this one, 1/5 here. So until theta is equivalent to n, then the distribution has this generic form, 1/n e to the minus x to the power of n here. So in this case, we cannot pinpoint to a certain alternative distributions, okay? So it can be either this one, or this ones. So in this case, it becomes a composite hypothesis. Since under the HA or under the H1, under the alternative hypothesis, no specific exponential distribution can be specified, okay? In this case, I mean, it's also nice to know that the way that we prove this kind of things is more like, we prove by inductions mathematically. We call that proof by inductions, because we just show that, okay, this is the example for theta 3, theta 4, theta 5. This is the form that it will take. So theta equivalents to n. This is the generic form, or the general form of the PDF that it will take. So we prove things mathematically speaking by inductions. Okay. So we proceed to another example. Suppose that we have another random sample, x1, x2, and xn, but it's not from the exponential distribution. It comes from another distribution. It's a usual normal Gaussian distributions. It's equivalent. It's either normal or Gaussian distributions with mean, mu, and unknown variance sigma squared. Is this hypothesis HA mu equals to 12 a simple or composite hypothesis? So in this case, we specify the mu or the mean parameters for this Gaussian distribution or normal distribution, but we haven't specified what is the variance for these distributions because we assume that the variance is unknown. So is this considered a simple or composite hypothesis? Okay. So in the example 3, so we need to extract the key informations from the questions. So there are 3 key information in here. Always do this if you want to solve solve a questions. First one is x1, x2, all the random samples of these observations comes from a Gaussian normal distributions. And the second point, we know that the mean the distribution is given by is defined by 2 parameters, which means equivalent is equals to mu, and the variance is unknown, sigma squared. Mu is, and then we already know, we already specified distributions. One of the distribution parameters, which is the mu or the mean, is equivalent to 12 under the alternative hypothesis. Okay, so is it a composite or simple hypothesis in this case? So recall that the probability density function for a Gaussian distribution or normal distribution is given by fx. Fx given your mu parameters and your sigma squared parameters, your variance and your mean parameters. And this is the PDF function for this one. Again, the range of the values that can be taken by your x is between the minus infinity to positive infinities. These are the bounds for the values that can be taken by x. And the sigma squared, because your sigma squared or your variance is always positive, so it's more than zeros. And then the mu's can also take values between minus infinity to positive infinities. Okay, let's see whether it's simple or composite hypothesis. So when HA mu equals to 12, then distribution under the alternative hypothesis is given by this one, the PDF of the normal distributions, where you substitute the 12 there into your mu here. Okay, and then you leave all the all your sigma all your sigma values, all your sigma symbols there, because you don't really know the values for your variance. So in this case, the distribution is not fully specified because we don't specify the variance or the dispersion parameters for the normal distributions. So that's the reason why the sigma squared is still there. The sigma is still there. So in this case, the full specification of this normal distribution is incomplete. So we don't really know what is the specific distributions for these normal distributions under the alternative hypothesis. So in this case, mu equals to 12 is a composite hypothesis. But if you know that the population variance, for example, like 12, 24 or 10, for example, then you can substitute the values into this one, into the sigma parameters there. So now it becomes a simple hypothesis because you specify the values for both parameters. But if you don't specify the values for all parameters, then it becomes a composite hypothesis. So in this case, we can say that for a distribution that have like 2 parameters, like mean and variance for normal distributions, you need to specify both parameters before the hypothesis become a simple hypothesis. If it only have like one, it only has like one parameter, if you just specify one parameter, that will be sufficient. But the main gist is you need to specify both parameters before it can be considered a simple hypothesis. Okay, now let's move to the best critical region of size alpha. So we start again with a simple definitions. Consider a null hypothesis where your null hypothesis H0 is where the parameters values, the theta here is equivalent to some values of theta naught, against an alternative hypothesis where the theta values is equivalent to some theta alternative there, some other values besides besides the theta naught. Let's see and D be the critical regions of size alpha, which means that the alphas is equivalent to some critical region of size C under the null hypothesis, and then alphas equivalent to the critical regions of size for sure is size alpha of another critical regions D, given the null hypothesis as well. Then C is the best critical region of size alpha if the power of the test at theta under the alternative hypothesis is the largest among all hypothesis tests. To show this further, let me go back to this diagram. Okay, so for example, if we fix the alpha there, okay, with certain values, we need to find a region that can minimize the beta here, your type 2 error. If you minimize the beta here, then you optimize or you maximize your 1 minus beta. If you maximize your 1 minus beta, so it means that it maximizes your power. So the duty is to find a critical region or define a critical value, because the critical value will determine the critical region where the power can be maximized and then the type 2 errors can be minimized while fixing the alpha type 1 error. There will be lots of critical region. There will be lots of critical regions that you can define there, but there will be one critical region where the powers is at the maximum. Okay. For example, if you fix alpha here, there will be like this region perhaps is where the powers of the test can be maximized, and then the type 2 errors can be minimized here. So that's what the definition is all about. Okay. So more formally, C is the best critical region of size alpha if for every other critical region of region D of size alpha, the power under the critical region of C, given the null hypothesis, is bigger than the power for other critical region. That is, C is the best critical region of size alpha if the power of C is at least as great as the power of every other critical region D of size alpha. And then in this case, we may assume, or we may say that C is the most powerful test of alpha size. Why is most powerful? Because it maximizes the 1 minus beta, the power of the test, while minimizing the type 2 errors, your betas, and then while, at the same time, at a fixed type 1 error rate of alpha. In this case, in the usual case, around 0.05. Okay. So before we proceed further, because there are lots of theoretical works that we have covered, I just want to give you some brief introductions. I mean, who are the proponents or the ones who propose the Neyman-Pearson Lemma? It's actually proposed by two people. It's proposed by this person, Jerzy Neyman, a very famous statistician from Poland. He passed away on the day on the year where I was born, 1981. He's a very famous statistician. Lots of things that he discovered, and one of it is a Neyman-Pearson Lemma. And then by another person, and then it's also a joint work by another person, another famous statistician, who was Egon S. Pearson. As you know, as you can see from here, the Pearson here, I think you are very familiar. The name with this surname Pearson, like Carl Pearson, the Pearson correlation coefficients, all those things. He's actually the son of the famous Carl Pearson, and that he passed away 1 year before Jerzy Neyman. Both are very famous persons. Okay. So for the Neyman-Pearson Lemma, suppose we have the definition for the Neyman-Pearson Lemma. Suppose that we have a random sample, x1, x2, x3 until xn, from a probability distribution with parameter theta, and the probability distribution can be either your probability mass functions or your probability distribution functions or your probability density functions given by a parameter theta. And this theta is actually it's not scalar, it's a vector forms. I mean, it can be like 2 or 3 parameters. For example, if a theta here is for exponential distribution, so it's actually a scalar, where it's only for the theta, the scale parameters, or the lambdas for the for the rate parameters, or it can be your means and variance for the normal distributions, or other things. Like it can be like 3, for example, like 3 parameters Weibull distributions. It can be up to 3, or for certain distributions. So then, if C is a critical region of size alpha, if they fix a type 1 error to a certain size, 0.05, and K is a constant, such that the likelihood of the parameters under the null hypothesis divided by the ratios, okay, the ratios of the likelihood under the null hypothesis to the to the likelihood under the alternative hypothesis is less than or equivalent to K, then we can say that it is inside a critical region. So in this case, we reject the null hypothesis or the H naught. So in this case, we can say that the likelihood is greater under the null hypothesis because this one should be bigger than this one for for the case to be less than certain values. So the likelihood under the null hypothesis is bigger than the likelihood under the alternate oh sorry so the alternative the likelihoods the likelihood of the likelihood of the null hypothesis is smaller than the likelihood under the alternative hypothesis, and because of that the K becomes very small. So in this case, then we will be in the critical regions. So then it's sensible because the likelihood of the null hypothesis is smaller than the likelihood under the alternative hypothesis. So when it's inside the critical region, so we reject the H naught. So if the likelihoods, if in the other scenarios, if the likelihoods under the null hypothesis is bigger than the likelihood under the alternative hypothesis with the parameters of theta equals to certain values under the alternative hypothesis, then for sure, because the numerator is bigger than the denominator, then it will be bigger than the K. So the values will be outside the critical regions. So in this case, we accept the H naught. Okay. So this is the notation that we use for the Neyman-Pearson Lemma for our class. But as you go along, sometimes when you read like the stats journals, you read like mathematical journals, like mathematical statistics journals, some authors, they swap this, they use like, instead of likelihood of thetas, which is the original notations under the Neyman-Pearson Lemma, they use like a likelihood of theta 1 will become the numerator, and the likelihood of theta 0 will become the denominator. So you need to swap this, you need to change the sign there. So if it's if they use L, okay. Right. Okay. So if you swap the sign, if you swap the L under the alternative hypothesis to the numerator, and then the denominator to the and the numerator to the denominator there, then it will become bigger than certain K before you can declare it inside the critical regions. But for the ease of our lectures today, just stick to this to these forms of the notations. But based on my experience, some other authors, they use different notations, but which is equivalently valid. So in this case, then C is the best. That is the most powerful critical region for testing the simple null hypothesis. Theta equivalent to certain values under the null hypothesis. Again, the simple alternative hypothesis, where theta is equivalent to certain values under the alternative hypothesis. Okay, sorry. Again, when I approach somebody there, then I cannot move my slides. It's Dr. Natri there. Hello. Okay, let me continue, and then I need to ask Dr. Sanson helps to help me with the slides. So in other words, Neyman-Pearson Lemma can be considered an optimum test is a uniformly most powerful test given a significance level size alpha. For the last points, it means that the Neyman-Pearson lemmas can also be considered for a composite hypothesis, right? So if we manage to obtain a critical region where for any sets of the alternative for the values of HA, which means that it can for exponential distribution can be the HA can be 2, 3, or 4, or 5. But if we manage to find this critical region where we can preserve the power for all the values of the parameters under the alternative hypothesis, then this one can be considered as a uniformly most powerful UMP test, given a significance, given a certain rate of type 1 error alpha, which is equivalent to 5%. Okay. So how can I move this one? I cannot see my cursor. Sorry, I cannot move my. I think next time I shouldn't like approve the what call that, the annotations. Okay. Right. Okay. Okay. Now we moved. Okay. Sorry about that. So to summarize everything in a simpler way, so you can see we can represent our Neyman-Pearson lemma in this simple graphs, for example. So again, this is our null hypothesis distributions, and then this one is our alternative hypothesis distributions of the parameters under alternative hypothesis distributions, and distributions of the of the parameters under the null hypothesis distributions. So in this case, we specify the null hypothesis values for the mu, which is equivalent to 3, and then mu for the alternative hypothesis as 4. So we also know that certain values for the variance, which is in this case, we fix the variance to 1/9, or your standard deviations of 1/3 or 0.333 something, right? So it's a fully specified distribution. So it's simple hypothesis for alternative hypothesis. So, okay. So if you have like a random samples, a random observations of x1, x2, x3 until xn. So in this case, if the values of the means that we obtain or the test statistics we obtain lies under this region here before the critical value there, so it means that it lies under the null hypothesis distributions, most of them. And then these ones will be your usual size alpha there, which is 0.05, the type 1 error. This is your null hypothesis distributions. So in this case, if we manage to find a Z statistics, for example, around these regions, for example, so we can say that the likelihood of the X under the null hypothesis is greater than the likelihood of the X of the observations under the alternative hypothesis. And because of this, the what call that, the ratio here becomes large. So when it becomes large, the values, the ratio will be, the likelihood ratio test here will be outside the critical region, will be around these regions. So in this case, we cannot reject the null hypothesis, or we fail to reject the null hypothesis. Okay, so we retain the null hypothesis here. So, but what happens if this is in the other case? For example, we obtain, based on our observations, we get the different results. In this case, we get Z statistics around these regions, showing that the mu or the parameter value is more than 4, for example, like 5 or 6, based on our sample mean, which is an bias estimator of our population mean. So in this case, the ratio between the likelihood under the null hypothesis with respect to the likelihood under the alternative hypothesis is small. So when it becomes like this, then the values will be outside the the regions under the null hypothesis distribution, for example here, or even here, even though it's still under the lines of the null distribution there, but it's in the alpha region now. So we need to reject the null hypothesis, because the likelihood of the observations is is greater under the alternative hypothesis here compared to the alternative hypothesis. In this case, we reject the null hypothesis, and then somehow we accept the alternative hypothesis. That's the basis of Neyman-Pearson lemma. Okay, so it's now 10:50, nearly 10:50 now. So I will give you, your deserved 5 or 10 minutes break. Then we will start again at 11 o'clock. Is that okay? We'll proceed with example 4, and then I will show you. I will skip certain examples, like I will go straight to example 8, 9, and 10, where it will be relevant to your, to your exams or to your test later on. So I will show you how usually the mark schemes for these kinds of, for this kind of questions for Neyman-Pearson Lemma. Okay, so I'll give you like 5 minutes break. So we'll be back around 10, no, around 11 o'clock. Is it okay? Okay. Is it okay? 11 o'clock.
Okay.
Okay. So I just stopped sharing the slides. So see you at 11. Hello, Assalamualaikum. Can we start now? Already 11 o'clock. Hello, is it okay?
Okay.
Yes, sir.
Yes, sir.
Okay, all right. So we start straight away with example 4. Suppose that we access a single observation from a population with PDF of fx theta times x to the power of 10 minus 1, where the x values can be from 0 to 1, less than 0 to can be between bigger than 0 and less than 1, and the theta, the parameters values, is always positive. So find the test with the best critical region, or find the most powerful test with alpha or your type 1 error fixed at 0.005 for testing your null hypothesis where theta is equivalent or is equals to 3, and alternative hypothesis is equals to and under the alternative hypothesis your theta equals to 2. Okay. So in this case, okay, the way that you solve these questions, again, extract the most important information from the questions. For example, you check the hypothesis where your H0 is where theta is equals to 3, and then alternative hypothesis where theta under the alternative hypothesis, the parameter values is equals to 2. So both of them, they are simple hypotheses because we specifies the parameters well for both the null hypothesis distribution and the alternative hypothesis distributions. So in this case, we apply the Neyman-Pearson Lemma to find the most powerful test. So again, you use the Neyman-Pearson Lemma where you find the ratio between the likelihood under the null hypothesis where theta not equals to 3, and then ratio, and then the likelihood under the alternative hypothesis where the theta a is equivalent to 2. So in this case, you plug the informations into the PDF here, the density distribution there, and then in this case you will obtain this ratio. This one is ratios under the null hypothesis to the alternative hypothesis. This is your likelihood. Why it becomes like this? Just only because you only have one observations. You don't have like 2 or 3 observation, and that's the reason there's no like the big pi symbol there. So you only have this one. So 3x squared there, you divide by 2x, then you get 3 over 2x less than or equivalent to k. So these two, then you and then you can move all the all the numbers here to the other sides, and then it will be equivalent to x less than or equivalent to 2k divided by 3. So these things here is a fixed quantity. This is your k. So everything here should be should only contains fixed quantity. There's no random variables here. Okay, there's no x, all those kind of things. So the 2k over 3 here can be considered as c, where x is less than c. So this is where your case lies, or your c lies here. So in this case, you want to find the the critical regions for the C. So let's define our type 1 error. Alpha here is equivalent to probability of committing your type 1 error. So in this case, it's 0.05. The size of the region is 0.05. So this probability of type 1 error is equivalent to a probability of rejecting a true null hypothesis. So we reject the null hypothesis here, given the null hypothesis is true. So rejecting a true null hypothesis, the probability of rejecting the true null hypothesis. So the probability of rejecting the true null hypothesis is x less than c, because c can be considered our our critical regions here. So theta is equivalent to 3 under where the null hypothesis is true. So again, this will end up with this with this relationship there where it's 0.05. So the way that you find all this information, you need to do the integrations of the probability density functions of the values there. So in this case, you set the upper bounds of these integrations as C, and then the lower bounds of it as zeros. So you obtain with a simple integration, you obtain x equivalents to x to the power of 3, and then you substitute the upper bounds and the lower bounds, and then you minus the upper bounds and the lower bounds values, and then you will obtain that C equivalent to C to the power of 3 is equivalent to 0.05. So taking a cubic root of the of the equations, so you will obtain 0.368. So in this case, the NPL, the Neyman-Pearson Lemma, inform us that the rejection region of the most powerful test of hypothesis, where the null values is equivalent to 3 and the alternative values is around 2, is when x is equal to 0.368. So any x values that is less than 0.38, then we can safely reject the null hypothesis. And then this test the test at this level, at these critical values here, it can be considered as our as our most powerful test. I mean, it optimizes the power of the test, 1 minus beta, or is reduce the type 2 error to the minimum. Okay. So that's how you perform we call it the solutions for this kind of example. So I show you another example before we proceed to the exam questions. Okay. So in this case, we have another samples from another random samples, x1, x2, x3, but until xn now it's not a single sample now. It's not a single observation. I mean, we have multiple observations. It's a random sample of multiple observations from a Gaussian distributed quantity of interest or normal distributions with in a population of people. And then these normal distributions has parameter values of mu for mean and a variance of 16. So it's our job now to find the test with the best critical region, i.e. find the test with the most powerful test, find the region that has the most the most power with a sample size of 16 and a significance level alpha 0.05 to test the simple null hypothesis H0, where mu is equivalent to 10 against alternative hypothesis values of mu equals to 15. Okay. So in this case, okay, we extract the information, the relevant information. As you know, the PDF of the probability density function of the normal distribution is given by this form here. So the first information, we extract what are the values for our parameters under the null hypothesis. In this case, it's 10, mu equals to 10. And then under the alternative hypothesis, the mean parameters is equal to 15. And then the sigma squared, or our variance parameter, is equivalent to 16. So in this case, we apply our NPL, our Neyman-Pearson Lemma, the ratio between the likelihood under the null hypothesis to the likelihood under the alternative hypothesis. I mean, should be less than k when we reject the null hypothesis, when the values is inside the critical region. So we substitute the values is 10 for the parameters under the null hypothesis and then 15 under the alternative hypothesis. Because now it's not a single observation, it's a multiple observation. So the likelihood has these following forms where we have like big pi sign here. So the likelihood, because we have 16 observations, so this is the first observation, and then the upper limit of it is 16. So we just multiply the conditional distribution there of x1 given the parameter value of 10, parameter values of mu is 10, and then the variance of 16 for x1, x2 until x16. So in this case, when we plug in the sigma squared into the sigma squared 16 into here, and then we plug in the 10 and the 15 into the respective into the respective distribution, the null distribution for 10 and the alternative distribution for 15, mu equals to 15. Then we will obtain the likelihood of theta 10, where the values of mu is equals to 10. Then we obtain the likelihood in this form. Okay, so I stand the mu's and then this one your standard deviation, just a sigma there, and then 32, and then 32 here because you substitute at 16 there. Okay, so you obtain this one. So this one is the likelihood under the null hypothesis. The likelihood under the alternative hypothesis, you substitute the values of mu, 15 there, and then the same value for variance. So you obtain this form. But in this case, the only difference is the mu there, 15, because we're using the same, what I call that, the same variance of 16. So the ratio between the likelihood under the null hypothesis with respect to the likelihood under the alternative hypothesis is given by these forms. The only difference between this one is like the 10 there and the 10 there for the mu's under the null hypothesis, and the 15 under the alternative hypothesis. And then because I mean this one is a fixed values and the same, so you just cancel out all those things. So you will so only these things remain. And then in this case, I've been using a simple algebra where, I mean, these simple algebraic relationships. We perform all these algebras, and then we will the expression will be reduced to these following forms. Okay. So this one is 1,600 if you sum all these things up, because if we have like because this is fixed quantity, so 100 plus 100 16 times. There are 16 observations, so we got the 1,600 there, and then 225 you sum it up 16 times, so you got 3,600 there. So you just cancel out, you know, the terms that are the same, so you will end up with this one. Okay. You can. I mean, I will share with you the slides later on, and then you can see, I mean, how we will manipulate the equations, because I also put some notes here in terms of the algebraic relationships, where from these forms it will be reduced to this form. Okay, because we need to cut the explanation a little bit short, because I mean there are several things I need to cover as well. So when you work with this kind of expression, it's much better where if we work with the log forms. So we take log on both sides. So when we talk log on both sides, so we will obtain these following forms: minus 1/32 inside the bracket, and then which is less than ln k there. So you make some algebraic manipulation there, because you need to ensure that all the left-hand sides there, it only contains the random variables, and all the other fixed quantities will go to the right side. So you make some algebraic manipulation there. So we will end up with this kind of expressions. Yeah. And then we can because we know that n is equal to 16, which is we have like 16 observations, then we can manipulate the inequality as follows: divide both sides by 160 and cancel, because we are using the mean relationship there, because you know that x bar is equivalent to the sum of xi equals to n. All right. So if we manipulate this kind of, if we divide both sides here by 160, so we will get these following forms, just to simplify the algebraic relationships. So in this case, because we have 10 here, so we cancel out 0, so we have like sum of x of 16 observation here, xi, x1, x2, x3 until x16 divided by its sample size, which is 16, and then we will obtain, and then on the right hand side we obtain these expressions. Okay. Using the mean relationship, the sum of x divided by n equals to your x bar. So these left hand sides will become your mean there. So the critical region here is equivalent to x bar equivalent to or larger than these quantities, and this will be your C. So x bar here should be bigger than C before we can reject the null hypothesis there. Okay. One more thing. If you're confused why the signs change here, because we divide by negative there. So when we divide by negative, so the signs change, so it becomes bigger than here. So that's the thing. If you if you become confused why at the end of the algebraic manipulations there, the signs change. Okay. Okay. So we start with example 5. So we have another two more example 5. So in this case, we want to find what is our what call that our values for C's. Okay. So in this case, we can assume that alpha is equivalent to probability of our type 1 error. In this case, on the right side of the region for our normal distribution. So in this case, if probability of rejecting the null hypothesis given the null hypothesis is true. So the probability of rejecting the null hypothesis, as we have done before, we have seen before here. So is x bar equivalent to or greater than C. And then given the parameters values under the null hypothesis is 10. Okay. So using the z-score, the standard normal distributions of mu zeros, and then the variance of 1 or standard deviations of 1. So we just plug in the means into the x minus mu there, and then we obtain the the standard error there. So 16 is the variance, and then we divide that by the sample size, and then we square root, and we get the standard error, and then this equivalents to 0.05, and then p z bigger or equivalence to c minus 10 divided by 1 equals to 0.05. So again, we know that 0.05 one-sided, the z value for it is 1.645. Okay. So 1.645 equivalents to, on the left-hand side, c minus 10 divided by 1. So we move 1 to here. So 1.65 times by 1 becomes 1.6545. Then 6 minus 10 there. And then we move 10 to the other side, becomes positive. So the c is 11.645. So in this case, we know that the most powerful test occurs where the sample mean is more than 11.645. So it means that if the sample means values is more than 11.645, then we can reject the null hypothesis and accept the alternative hypothesis. Okay. So that's the thing. Okay. So what will happen? So for the second part, if you want to find the power of the test when the values under the alternative hypothesis is true, in this case, mu equals to 15. So the first thing is we need to find the type 1 error, because the type 2 error, because type 2 error, because the power of the test is 1 minus probability of committing type 2 error. So in this case, probability of type 2 error is equivalent to probability of accepting the null hypothesis when the alternative hypothesis is true, okay, or when the null hypothesis is false. Okay. So in this case, probability of accepting the null hypothesis when alternative hypothesis is true, or probability of accepting the null hypothesis when the null hypothesis is false. So in this case, what is the probability of accepting the null hypothesis? The probability of it is less than 11.645, because we reject the null hypothesis when it's more than 11.645. So when we accept the null hypothesis, the value should be less than 11.645. Given the mu now under the alternative hypothesis is 15. So using like the z value, the standard normal values, then we can obtain, we will obtain this this quantity here, 11.645 divided by 15, and then divided by minus 15 divided by its standard error. So we'll obtain the probability of committing type 2 error as z value less than minus 3.36, which is equivalent to 0.0004. Okay, this one is the probability of type 2 error. So what is the power of this of the test? The power of the test is 1 minus type 2 error, as I showed you before in the graphs. So 1 minus beta. So 1 minus 0.004, it will become 0.9996. So you have, for this test, using these critical values and defining using this critical region, you will obtain around 99.96% power, which is a very high power. Okay. So I'll skip example 6 and 7. We can go through it later. Then we move to example 8. Okay. Because example 8, example 9, example 10, I mean, there are like, examples from past questions, questions from the past papers. So this question is one from the past papers. So in example 8, suppose that we have a random sample of 5 observations from a PDF, a probability density function of y the observations given beta, given the parameters, only one parameter here. So it's given by these forms. Do you know what is this form? This is Poisson. It's a Poisson distributions. Okay, it's a Poisson distribution. So it's not probability distribution function. Sorry, it's a probability distribution function, or your PMF, because Poisson is a count data, so it's discrete values. So it comes from Poisson distributions. We'll know that this one has a Poisson distributional form. So in this case, we need to test that the alternative hypothesis where the betas or the rate parameters for the Poisson distribution is equal to 5, and then versus alternative hypothesis where the rate parameter we assume is more than 5. Okay. So in this form, the alternative hypothesis has a composite hypothesis. But for A, we assume that beta is equivalent to 8, which means that is a simple hypothesis. For the alternative hypothesis, show the best critical region is y bar more than or equals to C. So there are 8 marks there. So the way we do this, for example 8, so we have like 5 observations, so y1, y2 until y5. Then we know that it's distributed Poisson with a rate parameter beta. So in this case, it's also equivalent to say that yi given beta is distributed Poisson beta there, where I is 1, 2, 3, and to 5, which is the indicator variable of the number of observations there. So we put the PMF or the probability distribution function as this one, the generic one. So we obtain the likelihood of the parameters beta, the rate parameter, as this one, where you have to multiply y1, I mean the conditional distributions y1 until y5 there, and then you will end up with this form for this likelihood. Okay, for the likelihood of beta. This is the generic form of it, likelihood of beta. So you will get 1 mark if you get the likelihood correct there. So now we start testing the beta is under 5 or under 8. So we put it using the Neyman-Pearson Lemma. We put it a likelihood under the null hypothesis as 5 there, and then under the alternative hypothesis as 8. It's less than C or K. It's up to you what kind of things that you want to use for the constant there, and then you will get another mark there for putting the right Neyman-Pearson lemmas ratios. And after that, you substitute the correct likelihood into the null hypothesis and alternative hypothesis. You will get another mark if you put the correct null likelihood, and then you get another mark if you put the numerator correct, the likelihood for the alternative hypothesis. In this case, because the betas or the rate parameters is 5, then we put a 5 there, beta there, 5, and then okay, sum of it is, we sum yi until 5, and then we put 5 beta equals to 5 for the null likelihood, and then we got this one is constant because it doesn't involve any beta parameters, so it's constant. So again, we do the same thing for the alternative likelihood for the alternative. So because the beta rate is 8, so we substitute 8 to the beta there, and then this one is sum to 8. So you cannot really see that, but it's actually sum to 8 there, and then this one betas is 8. So this one is also it's also 5 there, so it's a constant. So we just can cancel it out. So in this case, after you perform some algebraic manipulation using this algebraic identity, you will end up with this one. Okay, with this expression here, right? So when you arrive at this stage, you need to take a natural log on both sides. So you will end up with this log likelihood form, we call that, or log forms of it. log likelihood ratio test, whatever you want to call it. So you will end up with this one, and then if you get it correct, you get another mark there. So you may perform some algebraic manipulation there, and then if you end up with putting all the fixed quantities on the right side, and then leaving all the random variables quantities on the left side, so you will get another mark there. All right. In this case, you have to be beware. You have to be very careful. There's a change of signs from less or equivalence inequalities there to bigger or equivalent inequality in the next lines, because when you divide ln 5/8, it becomes is a negative number. In this case, it's around minus 0.47. So when you divide with negative, so the signs will change. So so you need to be very careful, because lots of students make the same mistake, makes lots of mistakes here, because they don't think that log 5/8 is negative, so they just retain the sign like that. So if you just retain the sign like that, so you will not get any more marks with this one, because you only be awarded the marks if the inequality sign is correct, and then all the other quantities are correct as well. Okay. So using the means relationship, so it's equivalent to 5 y bar there. Since this is the mean this is the main formula, so y bar will be equivalent to this one. Okay, if you bring this one down here, so become this one. So as you can see from the right hand side, all the quantities there, they are fixed quantities. Fixed quantities means that it doesn't contain any random variables. There's only one variable there. The variables is only on the left hand side of the equations. So you can say that all these things is a fixed quantity, which can be represented by your C star there. So in this case, we complete the proof, and then you will be awarded a final mark if you obtain the correct the correct quantity at the end of the proof. So in this case, we prove that 1 minus 1 bar y bar there is equals or greater than C, where for the best critical region. Okay. So for question B, suppose H0, the null hypothesis will be rejected when y bar is equivalent to 6, equivalent or greater to 6. Find the probability of type 1 error alpha. Okay, so in this case, our job is to find the probability of type 1 error alpha, and in this case, we have like 5 marks. So how we can do this? Okay, so probability of committing type 1 error is given by alpha there. So alpha is the probability of committing type 1 error, which is equals to probability of rejecting the null hypothesis when the null hypothesis is true. So in this case, we reject the null hypothesis where where the y bar or the mean is more than 6. Then given the rate parameter equals to 5. So if you get this relationship correct, if you define the probability of committing type 1 error correctly, you're using this probabilistic relationship, then you will get 1 mark. And then if you put or include the right numbers or the right values for rejecting the null hypothesis here, and then the betas or the betas values for the null hypothesis, when we assume the null hypothesis is true, you will get another mark. Okay. So in this case, to make things much simpler, we can use a normal approximation to Poisson. Okay, as you know from your previous studies, that the sum of Poissons will be Poisson as well, and then the mean of the Poissons of the variable will become a scale Poissons. You can see the side lemma here and the formal proof there. So we can say that okay, the y variables somehow, it can be distributed as a normal distribution, because we now assume the normal approximation to the Poisson distributions. So the normal distribution, they have like 2 parameters, the mu and the variance parameters. Okay, the mu and the variance parameters. So as you know that for the Poisson distribution, the variance and the means of the Poisson distribution, they are the same. All right, they are the same. So variance and mean, they are the same. So because we assume that the beta, the rate parameter, is the mean of the Poisson distributions, and also the variance of the Poisson distribution is equivalent to 5 as well. So we assume that the mean of the normal distributions for the y, or the normal approximation for the y is 5 for the mu, for the mean parameter, and 5 for the variance. So in this case, we assume that distribution of y as the random variables. But we are not interested in the y. We are interested in making the inference in terms of the sample mean, which is the y. Because, as you can see, our values, our data are summarized by the y bar here. Before, when we want to conclude whether we want to reject or retain the null hypothesis, or when we try to find the critical regions. So in this case, the y bar, as you know, is the distributions of the sample mean. So we want to find the parameters of distribution of the sample mean. So the distribution of the sample mean, is either the random variables or the mean. I mean, it will be the same. So it will return 1.5. But you have to know that the distributions, the variance of the distribution of the sample mean, is given by beta, or the variance, the usual your variance divided by the sample size. So 5 divided by 5, your sample, because you have like the sample size is 5. So in this case, 5 divided by 5, you obtain 1. So the distribution of the sample mean is given by this normal distribution 5, with mean 5 and variance of 1. Okay. Okay. So the probability of committing type 1 error under the null hypothesis distribution is probability of having a z value greater than the cutoff there, which is in this case because we assume that the sample mean is 6 and above, so it's 6. So the mean of the sample mean is 5, so 6 minus 5. The standard error is given by the square root of 1 there. So we obtain a z values of 1. So if we assume that the means is 6 or 6 or more than 6 for us to reject the null hypothesis. So given the parameters of 5, then the probability of committing the type 1 error will be 0.1587, which is pretty big. So when this is more than 0.05, we can say that we cannot reject the null hypothesis if you use the same threshold. But in this case, we're not doing any conclusion from this, so we just stop there. So the probability of obtaining alpha or the type 1 error is 0.1587. So in this case, if you put the correct values for obtaining the for the z for probability of standard normal here, you will get 1 mark. If you manipulate the quantities here well, then we will obtain another mark. And then if you obtain the right values, the right probability value for this one, you will obtain another 1 mark. Okay. So in this case, okay, to obtain the probability here, you just simply take like 1 minus p probability of z less than 1, something like that. So we will obtain 0.1587. Okay. So that's how you do it for this question. All right, so we go to the next question. So using the information in part B, where we know that we're going to reject the null hypothesis when the y bar is equivalent to 6 or more than 6, we find the power of the test if H1 is true, or the alternative hypothesis is true. Okay, so power of the test if null hypothesis is true is given by this one, probability of rejecting the null hypothesis when the alternative hypothesis is true. So if you put the things in a correct manner, so you'll get 1 mark there. So if you substitute all this here with the right values, those are probability of rejecting the null hypothesis. In this case, we reject the null hypothesis if the y bar or the sample mean is more than 6, given the alternative hypothesis, the parameters under the alternative hypothesis distribution is equals to 8. So again, we can use normal approximation to Poisson distributions, where the Poissons, the original distributions is Poisson 8 under the alternative hypothesis. So using the normal approximation, we also obtain 8 and 8, because you know that the expectations of y is equivalent to variance of y, which is 8 for the Poisson variables, or for the Poisson distributions. So in this case, we can approximate the Poisson distributions using this normal distribution for y. Okay, so means equals to 8, and then the variance equals to 8. So again, for the sample mean, you need to be very careful. The mean is the same, but in here the distributions, the variance is given by the variance of the original random variables divided by its sample size, which is 5. So the variance, or the standard, we call that this somehow the variance of the sampling distributions of the mean here as 8 divided by 5. Okay. So after that, you need to obtain what is the z values for this one. So the z values is 6 in this case, because we assume that we're going to reject the null hypothesis when the y bar is more than 6 or equivalent to 6. So 6 here. So we call it the mean under the alternative hypothesis is minus 8. So the standard error of this, so you just square root of it. Just square root of this, so you obtain the standard error in these bits. So if you get these quantities correct, so you get 1 mark. So if you get the the final answer for this one correctly, so you get another mark. So there will be like probability of z more than or equals to or more than minus 1.58. You get another mark. Then to obtain the power of the test, so you need to obtain the we call that the you need to use this form, okay, which is 1 minus 0.0571, which in this case. So you obtain the power of the test is equivalent to 0.9429. Okay, so it's like 1 minus p less than or equals to minus 1.58 here, which is given by 0.057. So the power of the test will be around 94.29%, which is very close to the 95%. So so the power is adequate, or it's very high. Okay, so the last questions. So if we only have like 4 marks. So if the sample above have the following values, the 5 sample above have like 8, 6, 7, 9, and 10. Use the best critical region that we obtain in B and give your conclusion. All right. So in this case, we obtain the sample. The sample mean of the observations using the using the simple relationships. So you sum all the observation, the 6, 7, 8, 9, 10 there, and then you obtain 40, and then you divide by the sample size, which is 5, and then you obtain 8. So the y bar is equivalent to 8. So we'll get 1 mark there. So to obtain the rest of the 3 marks, so you reject the null. You need to state that you reject the null hypothesis if y bar is more than 6. That's what we give that's the reason why we give the information in B. So any y bar more than 6, we will reject the null hypothesis. So if you state that the original rules correctly, so we get another 1 mark. But you need to make some inference there, because you have to say that, okay, because the y bar now is equivalent to 8, and the 8 is for sure is bigger than 6, then we reject the null hypothesis. Then we get another 1 mark there. So we can conclude that beta is equivalent to 8, which means that the alternative, we call it the parameters under the alternative distribution is correct, not the parameters under the null distribution, which is 6. No, which is 5. Yeah. So 5 is false, 8 is correct. If we have based on these 5 observations of 6, 7, 8, 9, and 10. Okay, so we'll get 4 marks: 1, 2, 3, and 4. So remember, these kinds of questions, don't stop at the calculations there. You need also to make some statements to get the full marks. You need to state the original rules, which is we reject the null hypothesis if y bar more than 6. And then because in this case, we obtain, based on our calculation, we obtain the y bar more than 6, which is 8 in this case. So we reject the null hypothesis. But you shouldn't stop there, but you need to conclude that what is the parameter now? It's either 5 or 8. Then you need to conclude that, okay, based on these observations, we can conclude that beta is actually 8, which is true under the alternative hypothesis. So in this case, perhaps we can reject we can reject the null hypothesis, which because the parameters under the alternative hypothesis is true. 1 mark there. Okay. So we move to the next questions from your past years. This is the example 9. Suppose in this case we have 3 random samples of x1, x2, and x3. It's given by a density function here, alpha x to the power of alpha 1 minus 1, where x will take the values between 0 to 1, and alphas will always be 1 there. Because we need to ensure that the density will not become zeros, because if we put that alpha equals to 1, then this one becomes this one becomes zeros. So any values here, and then we put alpha here as 1, so we will always get 1. So it will not be a proper probability density functions. So in this case, the Neyman-Pearson Lemma best critical region, we need to find the Neyman-Pearson Lemma best critical region to test H0 where alpha equals to 2 against H0 alpha equals to 3. Okay. So the solution for this one, again, it's a simple hypothesis. All right, simple hypothesis. So we need to specify the hypothesis H0 alpha equals to 2, H1 alpha equals to 3, and then we need to show how to obtain the generic or the general likelihood functions for the parameters. So in this case, because we have like 3 observations, so we're multiplying like the conditional distributions of x1 given alpha times by conditional distribution x2 given alpha and x3 given alpha. Multiply all of this, and then we will obtain a general form of it of alpha to the power of 3 and then xi alpha minus 1 to the power of alpha minus 1 with a with the product sign here, with the product signs on the outside. So we'll get 1 mark when you specify the likelihood function correctly, and then when you obtain a general form of the likelihood function, you will get another mark. Okay. So when you define the right Neyman-Pearson lemma, in this case, the likelihood under the null hypothesis, which is alpha equals to 2, divided by the likelihood under the alternative hypothesis, which is alpha equals to 3, less than or equals to k, then we'll get another mark there. To obtain another mark, you need to put the right values in the general likelihood form. So you put like 2 there, so you get 2 to the power of 3 and 3 there for the alternative for the likelihood under the alternative hypothesis. So become the 3 to the power of 3. So in this case, you have like x1 xi without to the power of 1, because alpha there 2 when you substitute 2 minus 1 becomes up to the power of 1, and then 3 minus 1, it becomes to the power of 2, and for the likelihood under the alternative hypothesis. When you do it correctly, you will get another mark. Okay, using a simple algebraic manipulation. So this one, because they have the same power, so 2 over 3 to the power of 3, and then you can just simply cancel out the the square here, because it's the same thing, because they have like the same expression but different powers. So you will end up with this one. If you do it rightly, if you perform the right algebraic manipulations, you will get another 1 mark there. And again, as I told you, make sure all the fixed quantities on the right side, and then all the random variables on the left side. So in this case, we call that you bring this one to here. So you bring P to this side. Okay, you multiply by this product here on the right on the left side, divide, and then you divide by K on both sides. So you will obtain these expressions. I mean, the way that becomes bigger here, because I just swap because if you bring the product terms to this side, so it will be bigger than this one. So it's the same thing, the same quantity. So as you can see from this one, all the left hand side now becomes random. There are only contains random variables. On the right side, there are all contains fixed quantities. There's no random variables there. So that will be your K star, or will be your critical region. So that you will obtain 1 mark. Okay. Hence, you we call that the I forgot the xi here. So you hence the product term xi here bigger than k star there, where k star is a constant, is your critical region. So you will get another mark if you state here. Remember this one, xi, there should be xi here because I missed the term there. So therefore, okay, so what is the best critical region in our case? So the best critical region under the Neyman-Pearson Lemma is given by this rejection region. RR means rejection region, given by the elements within the sets where all where the xi is is equivalent to or more than k star, which is a fixed quantity. So we get another 1 mark there. So the critical region can be considered as your rejection region as well. So if you want to put it, if you want to write is a critical region or a rejection region, it would be the same. Because rejection regions means that it means the region where you reject the null hypothesis. In this case, we reject the null when the xi, the product of xi I equals to 1 until 3 is more than k star there, and then you will get another 1 mark there. So in this case, always state the conclusion because the conclusion will give you another mark. Okay. So that's how you solve the questions. Okay. So this is the last one. In terms of the examples, this is based on the based on the past year's questions as well. So in this case, I think let me see, 1, 2, 3, 4, 5, 6, 7, 8. There will be 8 marks. Sorry, I didn't put the marks there. I mean, when I give you the slides, I will put the total marks. So there will be 8 marks for these questions. So suppose that we now have like a random sample from a distributions. It's a n random samples, x1, x2 until xn. Our random samples are from a distribution with a probability density function of this one. Okay, where x equals to where x is more than 0, should be more than 0. Because if x is not more than 0, then the fx the density function will be zeros. If x if x equals to 0, if x equals to 0 or less than 0. So we only can get assume positive values for x. So in this case, our job is to find the Neyman-Pearson's best region to test the alternative hypothesis where theta under the alternative hypothesis equals to 4 versus theta a, not here, theta, so yes, theta a here, where theta equals to 3. Sorry. Yep. Theta, yeah, under the alternative hypothesis A, where theta a or theta alternative equals to 3. Okay. So in this example, fx is given by these density functions, and then we need to obtain the likelihood, the general likelihood form first. So the general likelihood form is given by this one. Okay, so this is density function of it. So after we perform some algebraic manipulations, so it will end up with this one. Okay. So this is the likelihood for the parameters theta. So again, we need to specify the Neyman-Pearson lemma, which is the likelihood of the parameters under the null hypothesis. In this case, the theta is equivalent to 4, and then under the null hypothesis, and the likelihood under the alternative hypothesis where theta equals to 3. In this case, and then the based on Neyman-Pearson lemma, this one should be less than or equals to k. So in this case, we plug in the values of the parameters the thetas into respective likelihood. So in this case, we put 4 in here, and we put 4 in here for the likelihood under the null hypothesis. If you get the likelihood under the null hypothesis correct, you will get 1 mark. If you get the likelihood under the alternative hypothesis correctly, then you will get another mark. Okay. After that, you will get 2 marks there, and then you perform some some correct algebraic manipulations because they have the same power here. Okay, we have same power here, so you can reduce this form, this 2 form into this one, and then based on the the same multiplication because this one based on the algebra based on some algebraic manipulation, you will end up with this ones, because this one is divided, so you need to minus you need to subtract the power there, so minus n divided by 4 minus n divided by 3, so minus we will get positive. So in this case we get 1 mark if you do it correctly. Okay, after you add up these fractions together, you will end up with this one. If you obtain the the final form before you take log on both sides correctly, you will get another mark. So you take the natural log on both sides and you perform some logarithmic manipulations. If you do it correctly, you will get another 1 more mark. And then again, remember, you need to shift all the fixed quantities to the right side, and just leave all the random variables quantities on the left side. So you move all the fixed quantities, the n you move first the n divided by 12 to the left side. So you will end up with this one. So we obtain 1 mark, and then you divide by the ln 3/4 on both sides. So you will end up with these quantities here. And remember, when the log is less has this fractional form, so it's a negative number. So when negative number, you divide something with negative number, then the inequality sign will change. Okay, because ln 3/4 here is equivalent to minus 0.28768. So if you get these following forms, then you will get another 1 more mark. To obtain the final mark, okay, you need to mention that hence we reject hence the critical region for using this Neyman-Pearson lemma is given by these quantities here, where the k star is a constant. So you get additional 1 mark. Or you can state it differently. You can say that we reject H0 when when the sum of xi is more than k star, i.e. the rejection region is given by the elements within the set here. You mean it's equivalent. So whether you state this one or this one, you will get one additional. You will get the marks. Okay. Because we still have the time. Because we still have the time there. So how about I showed you one final example, not the most not the one which is more complicated. This will be the last example. So example 6. Let's say that we have x1, x2, x3 until xn, a random sample from an exponential distributions where we specify the theta naught equals to 2 under the null hypothesis, and then the alternative hypothesis distribution is given by the parameters theta alternative of 1 there. So in our case here, we need to find the most powerful critical region of size alpha. So based on example 6, we know that the exponential distribution is given by the rate parameter by the scale parameter theta, where the probability density functions of the exponential distribution is given by this one. By this one. So we check the hypothesis is a simple hypothesis because we specify the full distributional forms, that specify the actual values of the parameters. So using the Neyman-Pearson lemma, so the likelihood under the null hypothesis is given by this one, and then the likelihood under the alternative hypothesis is given by this one. I mean, I just drop the product term there, but it's equivalent. It's equivalent. So it's less. It should be less than some constant k. So using the same the same recipes or it's the same ingredients that we have shown before. So we obtain the likelihood functions. The likelihood under the null hypothesis as this one, and the likelihood under the alternative hypothesis as this one. So we plug in the values for the parameters under the null hypothesis and the parameters under the alternative hypothesis. So we will obtain this following form here, because the values under the null hypothesis is 2, theta 0 equals to 2, and the alternative theta alternative is equals to 1. So we have this form. So using some algebraic manipulations, So we will end up with this expression because this one has the same power. So again, we'll end up with this one. So with some algebraic manipulations, minus and minus of this one. So you will obtain this one. So after some further algebraic manipulation here and then summation of this one, so we will obtain these forms. Okay, then we take log on both sides to simplify, the calculation further. So we will obtain this form. If you use some questions, if you end up at this form, you will get at least 2 marks. 2 marks for this one, 1 mark for this one, and then 2 marks for this one. And then if you perform the correct log and the correct manipulation, you will get another mark there. And then you bring everything, the constant values to the right side, and then retain all the all the random variables on the left side, and then you will end up with these expressions. Okay, so we end up this expression because this one is constant, so we consider this one as C, as our critical values. So the sum of xi should be less than or equals to C, where we can reject the null hypothesis, and this can be considered the most powerful region of size alpha. And then for example 7, you can go through yourself how to do it, because this one is more complicated. Not more complicated, but it takes more time to explain. So we don't really have much time because we're nearly like 12 o'clock now. So as a final words, just an acknowledgement that lecture slides had been provided by Dr. Muhammad Irfan, but I made certain modification to the slide and then certain words that have changed. And then in terms of the solutions, I changed it a bit here and there to increase the clarity of the explanations. Okay, so that's all for lectures today. And then if you have questions, feel free to ask me in the next 5 minutes. So I leave the session back to Dr. Muhammad Irfan then.
Okay, thank you very much, Dr. Muhammad Irfan. So it's a very good lecture on Neyman-Pearson Lemma. Right, I hope all students can get some knowledge or extra knowledge from Dr. Irfan for your final exam preparation, right? Okay, so for the final remark, if you have any question, you can ask, unmute your microphone and ask Dr. Irfan directly. Any questions so far? Hello? No question? Serious no question, right? Betul lah, you all tak nak yang I cakap hari tu. Okay, so I think betul, I give you another 1 minute to think about it. If you have any question to ask regarding Neyman-Pearson Lemma. I think Dr. Irfan, there are no questions so far. So I think
that's fine.
I hope
you can share my my email address. I think if they want to ask me any question, then
okay,
I'm
we'll post
more
it
than happy. Yeah.
into
More than happy to
WhatsApp
answer it through WhatsApp group or anything. Yeah.
So if you later on you have any question, you can email straight to Dr. Muhammad Irfan, right? Regarding Neyman-Pearson Lemma, right? I think he will happy to answer the question for you, right? So I think are you going to share the slide, Doctor?
Yes, I'm going to share the slides, but there's several the things that I've missed in the in the solution, so I need to correct them, and then some of them in the questions as well, because I mean I forgot to make it superscript or subscript, all these things, to make it neater for the student to understand. Yeah.
Okay, thank you, Dr. Irfan. Once Dr. Irfan shared a slide, I will share it to you lah. Right. Okay, I think that's all. Thank you very much. Thank you, Dr. Irfan, for coming to our guest as a guest lecturer for our collaborative teaching, right? So I hope we will see you again on next semester as a collaborative lecturer again. Maybe I will give you more topic to give a lecture next semester. Right. Thank you, Dr. Irfan, and thank you all students. I think good luck for your final. Okay, Assalamualaikum.
Salam.
Thank you, Doctor.
Thank you, Doctor.